Chemistry time. Today we are talking about, let's turn the lights on. Today we are talking about chemical reactions. So, let's write that down. Chemical reactions. The abbreviation I have up there is one that you should become familiar with. I think you might remember from physical science, and really all of this should be reviewed from physical science at first, and then I'll talk about a couple of new things at the end. They aren't very they're not hard, but they are a little bit complicated. And so let's start first by reviewing what we should remember from physical science. There are 4 different kinds of chemical reactions plus a fifth, which is, the fifth one is kind of a separate categorization, but these are the types of chemical reactions. Do you happen to remember any of them? Or maybe you know them from your vocab. Or maybe being reminded of them by doing your vocab reminds you of doing them in physical science. Oh, no, but that is another one. We're going to talk about that too. And don't let me forget to talk about that because I often do. But the ones I'm talking about are like A plus B yields AB. Do you know what that one is called? Synthesis. This is a synthesis reaction. So when some chemical substance, remember, a pure substance can either be an element or a compound, but when some chemical substance, an element or a compound, combines with another separate substance, and they recombine to make a third separate substance, that's called a synthesis reaction. The reverse of that, AB breaks down into or yields A plus B, is called a decomposition. Right? It decomposes. Another type, AX plus B yields BX plus A, where the X has switched partners. The X is either cations or anions, but in the way I've written it is anion. This is called a single replacement. One thing has been replaced. Sometimes this is also called single displacement. I forget which one your book uses. Your book uses replacement. And then the third type is AX plus BY yields AY plus BX. Now they've both switched. A double displacement. Oops, sorry, double replacement. That's how your book describes it. And the examples for these are what we're going to do for our next lab. So you've done one example of a chemical reaction for your lab. You've done a lot of them in the laboratory, but for this chapter, you have done one. And then the next lab is going to be another example of each of these. So you'll have examples that you will do in the laboratory. So that's the first thing that we need to talk about that should be a review. By the way, let's write down the objective, which is model stability and change in chemical reactions. But my little rag went away. Stand by while I get another little rag. On the video, that's probably just going to come across as rah, rah, because I had to open that drawer that's really loud in there. Spray this. There we go. Would you remind me what I just said the objective is?
Model stability and change.
Model stability. I spelled stability wrong. And change I'm going to put RX in reactions, in chemical reactions. So this should be reviewed. These are the types, and you'll get examples of that as we go. But does the format of these types, does this make sense, do you think?
Yeah.
Okay. The other thing that should be reviewed is balancing. And there will be your chapter review has some practice you could do for balancing, but you'll also get a worksheet to practice balancing, and then you'll have the opportunity to do more worksheets to practice balancing, because this is something that you just have to practice to get good at. So you'll have one kind of brief mandatory one and then some optional ones too. So let's say trying to think. Let's use a specific one. Lithium plus water yields lithium hydroxide plus hydrogen gas. Well, so the point of balancing is that we need to satisfies the law of what? Why would we need to balance chemical equations to satisfy what law? That is when we're naming them, we do have to match the charges. And sometimes, and I may have even referred to that as balancing, that's not really balancing. This is balancing chemical equations. But we're trying to satisfy what law when we try to make sure that there's the same number of atoms of a particular one on each side. What law? Do you remember that law? Law of, yep, you got it. The law of conservation of mass. And so if we have one lithium on this side, we have to have one lithium on this side, which is already true. If we have two hydrogens on this side, we have to have two on this side, but guess what? There's three. By the way, this is vocab words, but this whole side is called what? Reactants, good. And this whole side is called the products. So what we have, individual atoms on the products have to match that same number of individual atoms on the reactants. So it isn't balanced. This right now is unbalanced. So we need to balance it. And we can only do that. Can I do this? Can I just make this into a 3? No, of course not. Of course not. That would, H3O does exist. It's the hydronium ion, but it wouldn't be in a chemical reaction like this. And we can't just do that because the hydronium ion is not water. They're not the same thing. We can't change the subscripts while we're balancing because it changes what it is. Right? LiOH is different from LiOH2, which doesn't exist. But if it did, it would be a completely different thing. Remember that the chemical formula of a compound has totally different properties. A chemical compound has totally different properties from the things that make it up. As an example, it's right here on the board, lithium is a silvery white soft metal. Water, you know what water is. You're drinking it right literally this second. Lithium hydroxide is a white solid, a crystalline solid. It looks like a white powder, kind of like the snow that's falling outside. And hydrogen is a gas, colorless gas. So these two things have completely different properties from these two things. That's one of the ways we know a chemical reaction occurred. And so we can't just go through and put in subscripts because it's different. It would be completely different stuff. So what do we do? What can we add? And what am I going to write in blue? Coefficients. Yeah. Yes, I know that's what you meant. Coefficients. And so I can multiply each thing by a certain number, by any integer, but that's all I can do. So if I want to get there to be the same number of H's on both sides, the same number of hydrogens in the reactant side as the product side, what can I do? Change my coefficient. So I can insert a coefficient. I can multiply this whole thing by 2, and now I have 2 lithiums, 2 oxygens, and 2 hydrogens. Altogether on the reactant side, or sorry, on the product side, I have 4 hydrogens, so I'm going to double that. And now I have 4 hydrogens, 2 oxygens on this side. And on this side I have 2 plus 2 is 4 hydrogens, 2 oxygens. But now I have 2 lithiums, so I just need to put a 2 here. And now it's balanced. So by multiplying all of those things by 2, or by multiplying those things that I did multiply by 2, I don't know why it made that noise. By multiplying those by 2, I have balanced it. I have made there be the same number of atoms on both sides. And what that tells me as a chemist is that this is the ratio of lithium to water. Not by mass, but by amount. For every 2 lithium atoms, I combine it with 2 water molecules to create 2 lithium hydroxide formula units and 1 hydrogen gas molecule for every one, right? If I did this reaction with just 2 atoms, obviously I wouldn't be able to see it, but I would do 2 atoms of this, 2 molecules of this, would yield me 2 formula units of this and 1 molecule of this. But that ratio is still true even as I scale it up. And when we talk about that later on here in chapter 11, that's called stoichiometry, the process of the ratio of certain elements in a chemical reaction one to the other. But this is how we balance, and it obviously gets both more difficult and more complicated when we get into more difficult and more complicated reactions. But that's just supposed to be an example refresher, because you should remember that from physical science. Now, the things that we are going to talk about that are a little bit, that should be new to you, that are not review, is the single displacement and double displacement reaction, the specific mechanisms of it. And it shouldn't take too long, but we're going to go into a little bit more detail. And so for a single displacement reaction specifically, single displacement reactions, we're going to consult the activity series, which in your book is on page 293. Mine has a little mark on page 293. Can you see if that's showing up on the camera? The little table, it is on the camera?
On the left or the right?
This here. I want this little table to.
No, go up and to your left.
Like that?
A little more left. Down.
Down.
Up, sorry.
Up.
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 There you go.
Okay. Well, you can pause it on that. I probably didn't leave it up there long enough. Good luck. But you can find that on page 293 of your book. So more reactive, we have two series, metals and halogens. We'll talk about the metals first. But in both cases, more reactive elements are on the top, and so they will replace ones below. So on that activity series, if we had, so this is only the case for single displacement. And so, well, this one actually, the one we just did is an example of a single displacement. And so if we didn't know whether this was going to happen or not, if I didn't give you the products, and I just had lithium plus water, well, is lithium, oh, this doesn't list hydrogen, so that won't work. Let's just get a new example, sorry.
What did you say?
Consult the activity series. Consult the activity series. Activity series. So let's say we had iron 2 chloride plus lithium. So this is all the information you would be given. A potential reaction of iron 2 chloride and lithium, will they displace? So this is all you're given, is that. Well, what we do is we consult the activity series, and we look and we see that iron is lower than lithium. And the rule is anything higher will replace anything lower. And so, will the lithium replace the iron? Yeah, it would. And so we can say that it would become lithium chloride, which would have this formula. We use the correct formula for lithium chloride, and iron. So basically, you kind of put yourself in the shoes of the chlorine. You from the perspective of the chlorine, you pretend you're the chlorine. Would you rather be with iron or lithium? Well, you'd rather be with something higher on the list, and since lithium's higher than iron, you switch. But now it's not balanced, so we do need to balance it. We would need a 2 here, and a 2 here, and so that is our answer. What about if you had, we're going to do another example, iron 2 chloride again, but this time it's being combined with tin. Well, look at the activity series. Iron is above tin. So if you're the chlorine, would you rather be with the iron or the tin? The iron. The iron. And so you were already with the iron, and so does anything happen? Well, no. The answer is no, RXN. No reaction occurs. So if the potential replacement is lower on the activity series, no reaction occurs. That's single displacement reactions. And like I said, that's not very complicated, but they do get a little bit tricky too. You just have to make sure you consult your activity series. And there's also one for the halogens. The halogens one is really easy. It's just the halogens in order from the top of that group to the bottom. The higher halogens, that is the halogens nearer the top, are more reactive, and so they'll replace ones on the bottom. Questions about single displacement reactions? Good? Your book then, you have this written down? Your book then talks specifically about combustion reactions, which now is a good time to talk about endothermic and exothermic reactions too. I'll do this in red. Your book lists combustion as another type, where it could either be a metal oxide or some carbohydrate, but basically something is going to combine with oxygen to produce usually carbon dioxide and water. If it's a metal, it'll be different, but this one is called a combustion reaction. And they can be synthesis. In the case of a metal, it would be a synthesis reaction. They can be single displacement reactions or even double displacement reactions, depending on what the X is. And that's why I kind of put it in a different color. But they are always releasing light and heat. And since they release heat, they are exothermic, which means releases heat. And since they release light or any kind of energy, they're also exergonic. Those words mean that it releases heat and releases energy, respectively. As opposed to, and I'm just going to do these in blue, because I think that'll be cute. Draw a line so I know we're not talking about combustion reactions anymore. Endothermic means it absorbs heat, and endergonic means it absorbs energy. All things that are exergonic, sorry, let me start that over. All things that are exothermic are also exergonic, because thermal energy, heat, is a kind of energy. And all things that are endothermic are endergonic for the same reason. But not all things that are exergonic are exothermic, and not all things that are endergonic are endothermic. Can you think of an example of something that is endergonic, that is, it absorbs energy, but is not endothermic, that doesn't absorb heat energy? Are there any chemical reactions that absorb another kind of energy besides heat? Photosynthesis. I'm thinking of photosynthesis. Maybe humans kind of do. I mean, there's a lot of chemical reactions that occur in your body. I'm sure some of them, I'm positive that some of them are endothermic, but I don't know if any are endergonic without being endothermic. But the one I'm thinking of is photosynthesis, which is, as you probably know, CO2, I did it in green because I think that's cute, CO2 plus water yield glucose sugar, and oxygen. And that takes light in. It absorbs light. So it's endergonic. Photosynthesis is endergonic. So we've talked about single replacement reactions. We've talked about combustion reactions. We've talked about endo and exothermic reactions. I'm probably going to erase balancing here, and we'll do the next thing over here. And that is, and this one will take the longest, and it's maybe a little bit complicated, but I think you'll get it and you'll do some practice with it, which will be really important too. But with double displacement reactions, the rule is, double replacement. I want to use the same words as your book. With double replacement, the reaction proceeds if a precipitate, which is a solid, or liquid, or gas, is formed from the aqueous solutions. So in a double displacement reaction, we're almost always combining two aqueous solutions. What does aqueous solution mean? Dissolved in water. Yeah, this is the letter A, lowercase letter A, lowercase letter Q. I did that kind of sloppily, and I want to do it neat. So we're usually combining two aqueous solutions, two solutions within water of different salts. And when they combine, if one of these three things is made, the reaction does proceed. The reaction does proceed. What does that imply? The reaction doesn't proceed what? The reaction doesn't proceed if one of those things isn't formed. like the single displacement reaction was no reaction if the replacement thing was lower on the activity series. This is no reaction if one of these isn't formed. And to find out if one of those is formed, well, in the lab we mix them together and we see if one of those is formed. But with the if we're just given the substances, we have to consult the solubility table, which we will get in a second. And to do that, once we do that, we use something called net ionic equations, and I'll show you that in a second. So I'm going to do the example from the book. It's a pretty simple example. HBr in aqueous solution, that's hydrobromic acid, plus NaOH in aqueous solution yields H2O, which is a liquid, plus NaBr in aqueous solution. First of all, step one is make sure it's balanced. Is this balanced? Well, let's check. On the reactant side, we have 2 hydrogens. On the product side, we have 2 hydrogens. On the reactant side, we have 1 bromine. On the product side, we have 1 bromine. On the reactant side, we have 1 sodium. On the product side, we have 1 sodium. And on the reactant side, we have 1 oxygen. On the product side, we have 1 oxygen. Is it balanced? Is it balanced? Yeah, it's balanced. The answer is yes. This is a balanced equation. So if it isn't balanced, the first step is you have to balance it. But this one is balanced, and so we're fine. The next thing we do is everything that is aqueous, we break it up into its individual ions. Which is, the way you can kind of remember that is that's what's physically happening in the water. So the water has dissolved HBr and made it into the H plus ion and the Br minus ion. It has dissolved the sodium hydroxide to become the Na plus ion and the OH minus ion. So we're just breaking all of these things up into their individual ions. Yields, we don't break up anything that is a precipitate, which is solid, a liquid, which is a liquid, or a gas, which is a gas. We don't break that up. So this is just, we just bring that down as H2O, a liquid. But we do break up this next one, Na plus in aqueous solution, plus Br minus in aqueous solution. So everything that is in aqueous solution, we break it up into its ions. Do you know what I mean by break it up?
Yeah, I tried to explain it, yes.
Okay, we separate it, and we write down the charges for each ion. Now the next step is we eliminate any spectator ions, and you'll remember that from your vocab. I'm going to do it in black. A spectator ion is one that wasn't changed in the reaction. So it's the same on both sides. Basically, just like in math, anything that's the same on both sides we can eliminate. What of these are the exact same on both sides?
Your sodium.
Yeah, sodium. So sodium is Na plus in aqueous solution here and here. So those both go away. I'm glad this marker is kind of dead because I want you to be able to see still. And the bromide ion. Yep. So what we're left with, now we just bring down what we're left with. H plus in aqueous solution plus OH minus in aqueous solution yields H2O, liquid. So question 1, did a reaction proceed? Did a reaction occur? Well, did we have a precipitate, a liquid, or a gas? Yeah, we did. In this case, we had a liquid. So yes, the reaction proceeds. And what is the net ionic equation? The net ionic equation is H plus in aqueous solution plus OH minus in aqueous solution yields water as a liquid. That's the net ionic equation. This one above, the one that we did as step 2, is the complete ionic equation. Should have thrown an equation on this one too. So the complete ionic equation has all of the ions. It's complete. The net ionic equation has only the ions that actually participated. No spectator ions. We don't write the spectator ions in the ion equation. And like I said, this example is pretty simple, and they do get quite a bit more complicated than that. And one other thing to remember that I don't show in this example is that any coefficient goes to both, and any subscript, if there were any subscripts, becomes a coefficient. Do you have questions? Okay. I think that's good then.
Sorry, did not mean to interrupt.
And you almost didn't.